Yes guys, today we're proving Nicomachus' theorem. So firstly, let's start off with what actually is Nicomachus' theorem. Well, it's the sum of the cube of natural numbers, so k cubed from k equals 1 to n. And Nicomachus' theorem says that this is equal to the sum of natural numbers squared. So we have the sum of natural numbers, k from k equals 1 to n, all squared. So essentially what this is saying is 1 cubed plus 2 cubed plus 3 cubed and so on and so forth is equivalent to, well, up to the n cubed of course, is equivalent to 1 plus 2 plus 3 up until n, all squared. So how do you prove this? Proof. So let's start off by saying, well, let's let Sn, so the sum of natural, equal 1 plus 2 plus n. This implies that sum natural, well, we know the formula n times m plus 1 over 2. Now we want to consider, so Sn squared minus s of n minus 1 squared, so the sum of all the natural number squared minus sum of all but the last natural number squared, and the difference between them. So using difference of two squares, this is equivalent to Sn plus Sn minus 1, and then Sn minus Sn minus 1. Now, Sn minus Sn minus 1, well, that is saying Sn equals 1 plus 2 plus 3 up until n. Sn equals Sn minus 1 equals 1 plus 2 plus 3 up to n minus 1. If we subtract them, well, we're just left with n. So we have n here. Now Sn plus Sn minus 1. How do we evaluate this? So we have, let's see, we have Sn is n times m plus 1 over 2 plus n minus 1 n over 2. What we can do, we can just take out factor of n over 2. Then we have, sorry, this should be a 1. n minus 1 plus n minus 1 plus n plus 1, all in brackets, all of that multiplied by n. Scroll down. So then we have n over 2 multiplied by n minus 1 plus n plus 1 is 2n, all multiplied by n. We have n squared in our square brackets, 2's cancel, n's multiplied by n, which is equivalent to n cubed. So now using this, well, what do we say? Alright, let's write that out again. Sn squared minus Sn minus 1 squared equals n cubed. So we've got one side of the proof, we've got n cubed. Now we need to just sort out this side. Well, if we write out what this actually looks like, so when n equals 1, 2, 3, 4, etc., etc. So we have, when n equals 1, we have, let's rub this out. Let's evaluate this. So s of 1 squared minus s of 0 squared, that's when n equals 1. We have to do this up until n, so plus s of 2 squared minus s of 1 squared. Let's do another 3 terms. S of 3 squared minus s of 2 squared. Let's go to the next line, plus, let's do s of n minus 1 squared minus s of n minus 2 squared plus s of n squared minus s of n minus 1 squared. Now this is a telescoping sum, so what we can do is cancel off the terms. So the s of 1 squared cancels from there. The s of 0 squared, well, s of 0 is just 0. Sum of the first 0 numbers is 0. Cancel that. S2 would cancel there. S3 cancel somewhere within there. And then there would be a s of n minus 2 here, which would cancel with this term here. S of n minus 1 squared equals s of n squared. So we can say that s of n squared minus s of n minus 1 squared equals sn squared. Which is quite good, because we also said that this was just equal to, let's go back up, n cubed. So hold on a minute, n cubed, let's go back up. Here's a mistake we made. When we meant n cubed, we meant as in the sum of every n cubed. But look where this came from. This came from sum of n squared minus sum of n minus 1 squared. So instead what we should write is, well, let's go back up here. Let's change this n to a capital N, capital N. So the first capital N terms, so Sn equals that, equals n cubed. And so n, let's just write up here, where n equals, what does n equal? One, two, three, up until, right, capital N that is. So if you go down here and we say n, n cubed equals Sn natural squared, and that is 1 cubed plus 2 cubed plus 3 cubed up until n cubed equals Sn all squared. And if we go back up, we said Sn was, what did we say Sn was? Sn was a sum of naturals. So you can work this out and say actually that could be capital. 1 plus 2 plus 3 plus 2 n all squared. I should clarify here that yeah, I just got mixed up with the n's and capital N's, but I think the rough idea of the proof is there. So yeah, all makes sense. Yeah, so over here, right, we were summing, it was what, from here. I think this is where the error lied. Should have clarified that here we were summing for when n equals 1, 2, 3 up to, so let's drag this down here. We were summing, oops, don't want to see Nicomachus. We just wanted to see, oh no, it's not coming up. Let's write here in red, sum from n equals 1, 2, 3 up until n. I think that's the part our proof is missing. Other than that, well, all good. That all makes sense. And yeah, this probably would have been, these n's here would have been all capital N's, and probably these n's here. Yeah, that seems a lot better now. Yeah, all good. Cool. Well, that's Nicomachus theorem for you. Goodbye.